So, okay. What I saw on the website was, what is a star? Why is the sun considered a star? How is it formed? Stuff like that.
Yeah.
Okay, so I'm happy to go through all of that with you guys. So, well, I think we're going to start a little bit farther back than what is a star, because if all we talk about what is a star, then you don't really see it in the context. You don't see how stars and planets come together, and you won't really have a sense of where the stars came from. So I'm going to start actually with the Big Bang itself, all the way back at the beginning of the universe. And at that level, it's kind of hard to visualize, but as we get closer and closer to the present day, you'll see it'll be easier to imagine in your mind what was happening. So our best theories of the Big Bang say that a very long time ago, 13.7 billion years ago, all the energy in the universe was combined into this one little tiny point in space. And then, for reasons we don't fully understand, it started to expand. And what that meant was that the density of it started to decrease because it got bigger. And after a few 100,000 years, the very first atoms were able to form, the actual very first matter. And as time went on, and as those atoms formed, they began to experience gravitational attraction to one another. And so we have a lot of theories about, we have a lot of knowledge about gravity. One of the fundamental questions, though, is why is there gravity? We can understand how it works. We can figure out if I drop my phone exactly how long it will take to hit the floor. But that's a different question than why is there gravity? That's not something we can go into today, and there really isn't a fully accepted, satisfying answer for anyone. But I just want to point out, we're not talking about the why, we're talking about the how. But the why is an equally interesting and separate conversation. So it's early in the universe, and the very first atoms are starting to form, and they're getting gravitationally attracted to one another. Eventually, enough of this stuff got pulled together that a process called nuclear fusion began. Now, you've probably heard about fission and fusion and chemical reactions. You maybe have heard about the periodic table of the elements. But at the most basic level, it turns out that when you have enough pressure pushing things together, typically from gravity, atoms actually combine. So two hydrogen atoms can combine to become one helium atom. And that releases a huge amount of energy in addition to creating a helium atom. And so that's actually the fundamental process that's going on inside stars. That's what really makes a star different than another kind of object, like a planet or what have you. So the beginning of the universe saw the first matter coming together, and then eventually the first stars. I forget how long, I think it was after a few million years. And so then throughout the very early universe, you had lots of new stars. You didn't have a lot of other stuff, but you had lots of new stars. And stars in general live about, I shouldn't say live, they're not alive, but they last about 4 or 5 billion years, depending on how big they are and how bright they are. A smaller star lasts longer than a bigger star. And the reason stars have a certain amount of time that they last is that when you don't look at the sun, but if you imagine the sun, what's happening is huge amounts of hydrogen is being turned into helium every second of every day. And you could look it up, but it's some incredibly large number, trillions of tons of hydrogen turning into, fusing into helium every day or every second. What really matters is that it's a staggeringly large number, but it is not an infinite amount of hydrogen in the star. So eventually, in our star's case, in the sun's case, after a few more billion years, the sun is not going to have much hydrogen left, and it's going to have mostly helium. And the helium is going to fuse and start to become lithium, and so on up the periodic table up until lead. Lead is the last element that is formed naturally in stars. Do you guys know about the periodic table?
Yeah, very, very little, I would say.
Okay. Okay, well, it's a really clever idea from about 150 years ago that puts all of the different types of matter uh, in an organized way. And one of the most basic ways by which it's organized is by mass. So the lightest elements are up on one corner and the heaviest are on the other. But the point is that the early stars formed because the very first matter in the universe, and all matter, but the first matter was gravitationally attracted to other pieces and eventually became a fusion reaction, which is what we call a star when it happens on a large scale. So that's what stars are fundamentally. And so this is all about 13 or 12 billion years ago, and the first generation of stars formed in this way. And there were big stars and there were little stars. They were all really big, but some of them were the size of our sun. Some of them were 100 times the size of our sun. I believe the smallest possible size for a star is 10 times the size of Jupiter. So if you take Jupiter, make it 10 times bigger, it will become a star. And the reason is that when something is that big and that much mass, the gravity is strong enough to start a fusion reaction. So it seems like when enough stuff gets together in the universe that it's 10 times the size of Jupiter, fusion begins and you have a star instead of something else. And actually, there's a lot of objects in the universe that are not quite that big, but they're too big to be planets. So they're called brown dwarfs, and they're these weird gas blobs that are not quite big enough to become a star, but are way too big to be anything else. So that's the first generation of stars. Now, you might be wondering about a couple of things. I've used the word first as if there was another generation of stars, which there is, and I haven't mentioned planets at all. And we'll get to planets, and the reason I haven't mentioned them is because I believe there's not much understood about the planets of the first generation of stars, and I'll tell you why in a moment. So after about 5 or 6 billion years, most of the first stars have ended, meaning they've run out of material to fuse, and they've either exploded or become black holes or become red dwarfs, or their lifetime as a star has ended. And those events are incredibly significant when a star either explodes or otherwise basically stops shining in a very literal sense. But what's interesting is that what happens there is that all the material in the star often gets spread throughout space. So if a star explodes, it blasts the material that was formed in the star, so the higher elements, the things after helium, hydrogen, helium, and lithium, those actually get blasted away, and they go in other places. And so you have other stars that form as a result of the end of life of the first stars. And I believe that in the universe today, we are in the middle of the second generation of stars, at least kind of at a high level. And that's where we get to the star we have that we orbit. So our sun is a second generation star, I think. And I believe most of the stars in the sky are second generation. And now we're going to get to planets. So in the early universe, there was not a lot of heavy elements. There was not a lot of iron and stuff like that that could become planets. So it was mostly the lighter elements, and they came together under their own gravity to become stars. But once that generation of stars died and those materials were released into the universe, they started to come together to make the second generation of stars, but also stuff that didn't make it into the star itself or that was left over. That's what became the planets. So as stars came together and formed, they have a lot of gravity, one, because they're holding themselves together, but also that gravity interacted with other materials. And as star material came together, you had other things starting to orbit the star. And in a lot of cases, they're really just gigantic rings of debris and elements, and they came together in a lot of cases to become planets. And that's why we have rocky planets and gas planets as you go out in the solar system. So if you look at our solar system, you have rocky planets that are heavy, meaning the materials in them are heavy, in the inner solar system. And then you have gas giant planets and ice giant planets farther out. Now, the outer planets are bigger than the inner planets, but the materials that make them up are lighter. So if you ever use a centrifuge, or even if you just if you take like a top, okay, like a spinning top, and you put, I don't know, I'm just making this up right now, by the way, but I think it would work. And you take iron filings and you put them on it, and you take shredded like Parmesan cheese or flour, you put them on the top and you spin the top, you'll notice that the iron filings don't go out as far because they weigh more. So the amount of force that you apply to them by spinning the top is not going to push them out as far as the flour. In fact, that would be a really cool experiment to do. But that's basically the same reason why you have rocky iron and rocky planets close to the star, and more gas giant planets farther away. So all of this is to set the stage for the discussion of how far away the star is, stuff like that. So we did just talk about what is a star, why is the sun considered a star. Before we go any further, I'll reiterate on that. So the sun is considered a star because it's a giant ball of fusion that's slowly turning hydrogen and other light elements into heavier elements. That's what a star is. That's why it's a star. So we talk about how it's formed, a little bit about the cycle of a star. What we haven't talked about is what happens as a star gets older. And let's say the hydrogen, there's less and less of it is made of hydrogen. So that depends entirely on the size of the star. So our sun is going to become a red dwarf, most likely. So what that means is that when, as time goes on and the sun is using up most of its hydrogen, in fact, in 1 billion years, the sun is actually going to change roughly in 1 billion years. It's going to start to change in a significant way. It's going to get hotter. And it's going to get hotter on Earth, too, because of that. And that's going to be a big problem for anything living here at that time. Now, another 2 or 3 billion years later, it's going to start to expand. It's going to cool down and expand. And that's going to be a big problem for Mercury and Venus and probably Earth, that may well get completely destroyed by the expanding sun. So, but what that's going to do is it's going to distribute the materials of those planets and the star into a circular disk shape from which another star might emerge. So there's this sort of cycle in the universe of stars dying, for lack of a better word, and then the material becoming new stars. So that's really how it's been going for the last 13 billion years. But that's a star the size of our sun, which is not very big. If you make it 100 times bigger, a star 100 times bigger would probably experience what's called a supernova, which is an extremely catastrophic explosion of a star. He gets it. That just massively blows all the material, or most of the material of the star, across the universe, which is an amazing thing to imagine. In human history, there have been several supernovas that were observed and recorded by older civilizations. They're so bright that they light up, that you can see them during the day. Imagine seeing something as bright as the moon during the day, but it's a star that is exploding.
Whoa.
Yeah. So, in fact, I believe there's some historians that think the Star of Bethlehem was actually a supernova. So, yeah, pretty wild. So that's supernovas. That's another way that the life of a star can end, depending on its size. And the really heavy, the really massive stars become black holes. And we could talk about that a little bit, but it's such a massive event when a star of that size collapses that it actually it breaks down the fundamental fabric of reality. Space-time itself kind of breaks or rips, and you have a black hole. Not a very good explanation, but the point is that stars are some of the largest individual objects in the universe, and what happens to them has extremely significant consequences, and that's why one of the reasons why we see them throughout the universe. They're that large. So getting to possibly what the whole point of this was, which is their brightness. Why do they look so bright? So I hope I've given you some kind of background as to why and how stars make light from the fusion reaction, where they are. They're all over the universe. And now we can talk about the relative brightness. So we're going to talk about some distances here, and they're going to very quickly get really hard to imagine. So if you think about let's start with the moon, how far away the moon is. The moon is 250,000 miles away. Sounds like a long way. I recently came up with a way to think about that in an earthly sense. New Zealand is about 12,000 miles away from Washington, D.C. And so going to the moon is like going to New Zealand and back 10 times, something like that, 20 times. So, 20 times. It's a really long way. Now you're flying a spaceship, not an airplane, so you go faster, but it's still a really long way. So 250,000 miles to the moon. The sun is 100 million miles away. So that is 400 times farther away. But it's much brighter, obviously, and it's brighter for a lot of reasons. It's a star, not a moon, and it's much bigger. Now, it is a complete coincidence that the sun and the moon look roughly about the same size in the sky. Complete coincidence. Now, you don't want to look at the sun anyway, but from Earth, they look about the same size. Doesn't mean anything. Now, when we look farther than the sun, if we look at other stars in the sky, if you look like at night, you see, depending on where you are, you could see thousands of stars. They all kind of look about the same because they're so far away that our eyes really just see a point of light. And that's due to a couple of things. One of them is the way the human eye perceives light when it's that far away. It always just looks like a dot. But those stars are actually, they vary from relatively close to our sun to thousands or millions of times farther away. Have you ever heard of an idea called a light year?
Yeah.
So it's a strange term, but it means the distance the light travels in a year. And that's a really long way. And the reason we use it is because otherwise the numbers just get too big. So the distance that light travels in 1 year is 6 trillion miles.
Whoa.
Which by itself is almost meaningless because it's so large. But if you start to think about where the closest other stars are, you can start to form a picture in your head of just how far that is. So the closest star to the sun is almost 5 light years away. So that's 30 trillion miles. You can see why we use light years instead of miles, because you can use a lot fewer of them. So there's other stars about 12 light years away, and all directions, by the way, not just one direction, because we're part of a galaxy that has stars all throughout space in all directions, and the universe is also has galaxies distributed in all directions. So there's a lot of stars nearby and a lot of stars far away, but they all tend to look the same to the human eye, except for the sun. So. But if you look at them with various types of telescopes, you see that some of them are extremely bright and some of them are not. And there's really no one rule. You could have a very large star that's a very long way away that looks just as bright as a dim star that's very close. Make sense?
Yeah.
So there's really no one way to look at it. The closest star to the Earth is actually not a very bright one, the sun, or a big one, but because we're so close to it, it looks huge in the sky, and it you can't see any other star during the day because of it, obviously. So I guess that sort of answers the question or addresses the point. The brightness of the sun and stars is due to their relative distance from the Earth. So that's sort of half true. The other half is and their size. It's not just how far away they are; it's how big they are. So I feel like that is a good kind of basic introduction into the whole idea of where the stars are and why they're there, what they're made of, what they're doing, and why they look, and how their brightness appears to us. So I can answer any questions. We can keep going.
What is it?
take something like a year to 10 to 100 years for us to notice a supernova that occurred?
Yes. Yes. So what you're referring to is the speed of light. So light does not move at an infinite speed. It actually has a certain speed that it follows. And when we see something in the sky, we're actually looking at light that's very old. So if you have a supernova, if you have a star that's 10,000 light years away, and you see it go supernova in the sky, that event actually happened 10,000 years ago. But we didn't see it until the light came to Earth and came to our eyeballs. And the sun, in fact, the sun is far enough away that it takes light 8 minutes to get to Earth from the surface of the sun. So if the sun exploded or stopped shining right now, we wouldn't know it for 8 minutes.
Yeah.
And so a lot of astronomy is looking into the sky and seeing how far away things are, and how bright they are, and working out what is actually happening out there.
It takes something like 80,000 years for light to the energy in the form of light from the nuclear fusion to reach the surface of the sun, correct?
Yeah, you're right. So the sun is a gigantic sphere, more or less, and the fusion, most of the fusion reactions happen in the center, and it actually takes a very long time for the light to get to the surface. Now, what's happening at the quantum level, which you particularly would probably be interested in, it's not the same photon that goes from the center to the outside. It's actually absorbed via collisions and re-released. But for imagination purposes, it takes that long for energy that's released at the center to get all the way out.
Thanks.
We've been watching a video, and one of the video tells them about this star named Betelgeuse.
Mm-hmm.
Is that star real?
Yes.
Correct.
It's a real star. I forget how it came to have that name.
That's what he said.
That's
He's
what
saying
I
he
read
read.
from the past.
That could totally be true. Some of these things are the history of this stuff goes back a long way.
Yeah.
Okay, here we go. So I'm looking at, the last part of the name, El-Juz, comes from Arabic, historic Arabic name of the constellation Orion, a feminine name in old Arabian legend. The beetle part,
Nothing to do with it.
I don't know. So it comes from Arabic. Anyway, it's a real star. It's a real name. I think it's a pretty huge star, actually.
Yeah, we were looking it up.
It used to be the biggest star.
They said it was the biggest star.
It was the biggest star.
Oh, yeah.
The Doris campus or something.
Yeah.
400 times the sun.
I see that. Something like that. It's if it was in the center of our solar system, the star itself would go almost all the way out to Jupiter. Yeah, it's really big. You can look up on YouTube scale of the solar system. There's a bunch of videos that show all this stuff next to each other, starting with like Pluto, really tiny, and getting up to these stars that are so big that they make our sun the size of a single pixel on the screen. So,
like the supernova exploded happened like 10,000 years ago.
Mm-hmm.
Is that the same for like a shooting star?
No. So a shooting star is actually is what we call a meteorite. A rock that falls into the Earth's atmosphere from space and burns up. So that's happening just a few hundred miles away. So that is happening right away, or instantly, almost. But your point is a good one, that it can be hard to tell what's happening near Earth and what's happening far away from Earth.
If the sun were to explode, how big would its explosion go? Like, how far would it go?
That's a good question. I believe the best answer to that question is that when it does start to expand, which it's not really the same as exploding, but I believe the theories say that it will expand to engulf, to be bigger than the orbit of Mercury, Venus, and possibly Earth. So it will get pretty big. But it will be less dense because it's a gas. I mean, it's a gas like the steam that comes from boiling water. So it expands. Really, the reason that stars the reason that stars have an edge, sort of, is the gravity, is it's actually holding all that gas together.
I'm looking at a video, and it says that there's one star that so the Earth minuscule to the sun, and right now they're zooming out and showing the sun next to a humongous star.
Yeah.
Is this I'm playing it right now? Is this the star? Betelgeuse. 88 Carinae.
Beta Carinae or Eta Carinae, yeah. Yeah, that's a big one. I forget how far away it is, but it's ridiculously huge.
Googling it.
I think our minds have been blown with how big these stars are because
Oh, yeah.
coming from a 10 and 11-year-old's mind, you're looking up in the sky and you think the star is like this tiny little, thing up there. So coming to find out that they're actually these ginormous things that are big.
Yeah, and even more amazing, to me, the sun, as a relatively modest star, is responsible for all life on Earth, which is currently, as we know it, all life in the universe. And we have life on Earth mostly because of the energy coming from the sun. And it's just a pretty average star, so who knows what's out there. I'm surprised no one is asking about aliens. Doesn't anyone in here care about aliens? Okay, thank you.
Do you believe in extraterrestrial life?
Who had just asked that? I couldn't see who was talking. Okay. So you're asking, everybody asked a question, and I'm glad everyone asked it because it gives me the chance to talk about a couple of really important ideas. The first one is belief itself, and the other one is life, alien life. To me, it's not really a question of whether I believe there's life out there. I can look at the data, the work that scientists have done, and I can make a guess based on that data, and that, to me, that makes me conclude that I think there is likely life out there, of some kind. And the reason is that so when I was your age, there were 9 planets that were known, and at that time we knew about 9 planets. And around that time, in the early 90s, NASA was working on a big telescope, a space telescope called Kepler, that after many years of work would look for planets around other stars. And now, 20 years or so later, we now know there are thousands of planets around stars near the Earth. In fact, we now think that most stars have planets, and many of those planets are close enough to the sun that there could be water, or at least not so close that it's impossible, and they're not far enough from the sun that it would be impossible. So the point is that we're discovering that there are planets everywhere we look. Millions, billions, trillions of planets out there. Around the time of the turn of the 20th century, so around the year 1900, we were just starting to discover the true distribution of galaxies, or maybe that was later. I think that was the 1930s. Yeah, it was the 1930s. In the 1930s, we discovered that the galaxy that we're in was not the only galaxy. About 80 years later, we're now discovering that there are planets around most stars in most galaxies. So what that works out to is trillions and trillions of planets throughout the universe. And if we look at our own solar system, we see water in a lot of places, ice in a lot of places. We see everything that we think life requires all over the solar system, at least in half a dozen places. And if that's representative of even a tiny fraction of the stars that are out there, that means there could easily be thousands of planets where life could exist, maybe even more. So then that gets to another couple of interesting questions of, just because life can exist, does it form? We don't know. And then another question, could we ever find it? Which is even harder. So those questions are to answer your direct question, do I believe that there is life out there? I am confident that there is, based on decades of research showing the huge numbers of stars and planets. So that's my answer. And I genuinely think that before 2050, we may know for sure that there's at least life in other places in the solar system. And if we find life on other planets in our solar system, to me that just almost guarantees that there's life around other stars, because if it came about in multiple planets around the same star, I mean, that just to me raises the odds that it happened around other stars and possibly around many, many stars.
About the alien thing,
Mm-hmm.
I don't know if this is true or not, but on the internet I saw there was an alien, so-called alien invasion, 15 something. I don't know.
Alien what?
There's like some kind of alien invasion almost on a farm place. I think there might be like, because they're like alien things.
Alien invasion where?
Like somewhere in the 1500s.
She's saying she heard in like 1500 there was like a.
Oh. Well, I'm not aware of any alien invasion that happened in the 16th century. I think it would be. I'm not inclined to think that could happen, because something like that would not, if that happened, would be so well documented that it would not be really up to debate.
I have like the people who did see this.
Mm-hmm.
I saw this on YouTube, so I'm not really sure if this is true.
Mm-hmm.
But they walked really funny in the back.
Mm-hmm.
The bullets that they shot at them seemed to bounce off of them.
Well, I would suggest that when you're faced with information about something that is such a big deal, that would be so world changing, if it was true, I would suggest that you follow the advice of I can't remember who it was. It was Einstein or Newton or somebody who said that extraordinary claims require extraordinary evidence. And to me, that means that the bigger of a deal that something is, the more likely I'm going to have seen it for myself to believe that it's true. So I would not personally take a YouTube video as evidence that aliens invaded Earth 500 years ago. I would rather see that evidence for myself personally. Only then would I be convinced that it actually happened, because it's such a big deal.
Kind of like Bigfoot.
Right. I mean, I'll look at a YouTube video and see what somebody had for breakfast. I'm willing to believe that. Okay, fine. They had toast for breakfast. I don't need to see that for myself. But something as important as alien invasion, I'd rather see evidence of that for myself with my own eyes.
Have you ever been to space?
No, I have not ever been to space. Yeah.
Is it true that like bluer planets are like more hotter than regular planets?
I think what you're getting at is the star temperatures. So bluer stars are hotter than redder stars. Redder stars are cooler. Yes. Yes, sir. Next question, and then I have to go, but I would be happy to do another session sometime. Sure.
Have you ever heard of Neil deGrasse Tyson?
Yes, he is a hero of mine. In fact, and I used to work for my former boss. I went to school with him for their graduate work. So yeah, I've heard of him. He's great.
Okay. So I googled VY Canis Majoris. So it's set on a website, not exactly reliable. I don't know, but it says VY Canis Majoris radius. That's enough. Estimates of the star's radius have previously ranged up to 2,000 times larger than the sun. The video that said 1 billion.
Gotta go with you.
That's okay. I'm happy to answer the question.
Anyway, it says if it was placed in the center of our solar system, it would almost reach the orbit of Saturn.
That sounds about right. Saturn is about 1 billion miles away from the sun. So an object with a 2 billion mile radius would actually be twice as far out as Saturn. An object with a 2 billion mile diameter would be out at about Saturn's orbit.
Okay, Ben?
Thanks.
Sure. Yeah. I mean, and just to say something in closing, this wonder that I hope you're all feeling right now, just at the scope and size of the universe and all the stuff out there, hold on to it if it really does something for you. I mean, it is when as you grow up you'll find you'll perceive pressures to kind of let go of it and like get a real job or like move on from it. But I would encourage you to hold on to it and see where it takes you, because it's been a great adventure in my life to be part of this kind of stuff. So don't let anyone ever tell you not to dream of the stars.
All right, boys and girls, what do you say to Mr. Nasrallah?
My pleasure. My pleasure.
Thank you so much.